I welcome you all to the 6 days virtual workshop on advanced characterization tools, fundamentals, applications. As we know, it is the fourth day of the workshop, and we are in the middle of this academic event. And today, we have a very eminent person and scientist as a resource person among us. I welcome you, sir, on behalf of our principal, staff, and students. I welcome you to this event. Dear participants, before inviting sir for his valuable talk, let me introduce him. Dr. Manoranjan Kar has done post graduation in physics from FM College, Balasore, Odisha in 1998. He pursued PhD from Department of Physics, Indian Institute of Technology, Guwahati, and the doctoral degree was awarded to him in 2004. His research area belongs to experimental condensed matter physics, nanomaterials, materials science. Dr. Kerr is reviewer of more than 30 reputed journals of international fame. He has published more than 130 research papers in highly reputed journals and 34 in AIP conference proceedings. He has presented his research work in more than 60 conferences and delivered more than 60 invited talks in various conferences and seminars. As a convener, he organized 8 schools and conferences. Till now, he has completed 3 research projects funded by various agencies, and 2 are ongoing. 9 research scholars are awarded with doctoral degree under his esteemed supervision, and 11 are pursuing. Also supervised 11 MTech students. His teaching experience includes teaching at UG level to BTech and at PG level to PhD, MSc, and MTech students. 2 scholars have completed SERB National Postdoc Fellowship under his guidance. He is the recipient of prestigious DAE Young Scientist Research Award, DST Young Scientist, and IAPT Best Teacher Award 2018. He has the responsibility of various academic and administrative positions in IIT Patna. He has joined IIT Patna in 2008 as an assistant professor in Department of Physics, and presently he is working as associate professor in the department. With this brief introduction, may I now request Dr. Kar to deliver his talk. Sir, it is up to
Okay,
you now.
thank you. Thank you, madam. And thank you, Dr. Panda. Or Panda. Hi. Okay, fine. So let me share the slide, then I can start my talk. And madam, by the way, how much time I have?
Sir, up to 1:30 in questions and all.
Okay, okay. Uh, Hello.
Yes, sir.
Just a minute. I'm
Yes,
sharing
sir.
it.
No problem, sir.
I'm not getting the screen here. That is the problem. Is it visible?
Yes, sir.
Fine. So both video and slide are visible.
Yes, sir.
Okay. Okay. Fine. I'm sorry. So it takes some time. So good afternoon to all of you. Uh, when I got the invitation, and it is not my research, it is just simple a class. So that will be better interaction rather having so many information. And definitely it is an electron microscopy, as you know, that it is going to be the our I can say that it is not fully matured, and it may be pretend to you that okay, we are in this era and it is electron microscopy, we will see it. And as you know that I cannot pass entire message within 1.5 hour, but still I will try to give the flavor that at least you will understand that exactly what the electron microscopy and it is doing, and what is the service it is giving to the science world, and how it has helped that to develop the technology. Not only we develop it and technology. So before going to it, as you know that, and the slides, some of you may have seen, it is my common slides that where I'm sitting, that I have to share with you. So this is our IIT, how it looks like, entry point, then our science building, and there are the other buildings, and this is inside our lab. So how we have arranged the different equipment like ACM, and we have low temperature facility and different characterization techniques. Then we have XRD and preparation unit, P loop, and hello, hello.
Sir, slides are not, sir, changing, sir.
Is it changing?
Sir. Yes, sir. Yes, sir.
So is it fine, or I have to go slide slow? Is it fine?
Uh, I think it is fine, sir. If participants have any problem, but they are not asking for any. Sir, you can go with this. Slide show
Okay,
is not
okay,
necessary. Yes,
okay,
sir.
okay, fine. So So these are the basically labs, equipment and XID and other things. Then we have the TM, it is the hub picture and also the VSM and other equipment. So we are well equipped. And before going to the talk, and it is my pleasure that to give the thanks to my collaborators and my students. They are the workers and my sponsor that who has given the money that to establish the laboratory, and I would like to thanks to them. And also I would thanks to madam and the college, all the faculty members, and also special thanks to Dr. Vatpanda. And always I'm associated with him since long, and also with madam, and I think a few years ago, and she contacted me. And also the thanks to the participant, because of you only they could arrange this conference, and also I could give the talk. So that's why always I give the thanks to the students and the participants, and mostly due to them, due to you only, and we could arrange it and just exchange the knowledge. So as madam told that, and we are working in the different materials in the different categories. Mostly the students are working in different problems. So in my means in my supervision, so we have some patents and as well as the publication and this thing, and some kind of experimental um, analysis and all we have proposed, and might be it will take some time to recognize. I think last time I was talking, and I don't know any of you have heard me about my research and all. So right now we are developing the theory, and one student is entirely he's involved there, and he has done already some of the work. It is yet to be communicated. So from the experimental result, we propose something, the theoretical analysis, and that is our achievement. If you ask me, last 20 years, that is our achievement, and we are going to establish it. So that theoretical modeling we are doing right now, although I'm a totally experimentalist, but recently one of my students have given this problem that we are trying to establish the theory. So that is the catering of my research basically interest. And if anybody wants to discuss anything, and always you are welcome to write a mail or call, and so that I can exchange the idea. So the topic today I'm going to enlighten you. Already it is 20 minutes has gone. It's for the schedule. So I'm sorry. And before going to that, and I will just tell you that why did I pointed out the 20 minutes, and it is important for all of us. So if you look at our ancient literature, that we say the Bhagavad Gita or something, and in some point of time, the people asked to the Krishna that can you give some time? Then he said that all of us are means poor on that the time. So that's what we have lost 20 minutes before going to the topic. I'm sorry for that, but I'll try to manage this. So basically, I will be covering that. We have to understand what is the classical limit. We will clearly understand what is the classical limit. Then should I go for the electron? Can I call it is the electron is in a classical particle, and some of the textbooks we keep on writing and these things. So we have to clear what is the classical limit. Why do we need to understand it? And for the electron microscopy, okay, why do we need it, the classical limit? So this electron microscopy, it is very, very important. First of all, I have to understand the micrograph when I get it, so that we will be clearing ourselves. Then what are the electron microscopy that we can build up, and as per the today's formulation or our realization, what are the electron microscopies that we can develop? And as you know, that means they are very limited, and don't panic, there will be not too much electron microscopy, and but I will be talking only two, and the third one I'm not going to talk today. So that is the transmission electron microscopy and the scanning electron microscopy. Maybe the question is arising that what will be the third one. There is a third one, electron microscopy, that is Auger electron microscopy, that we are not going to discuss, and only you will see that after the discussion. So you will be clear that how many microscopy I can build up with the electron source. Why it is the scanning electron and transmission electron are different? Those questions will be answering ourselves. That will be the talk. We'll be answering ourselves, and definitely I will show you some of the micrographs, how we analyze and how one can realize and these things. Those things I will be covering. I will go little fast because as you know that it is not a, means it is a course. Electron microscopy is a full 6 months course and it will be very difficult to pass, but I will try my best to give you the basic and realization. Before going to that, here it starts the first question: what is the classical limit? You look into this, and I have put it in the four. We have the four mechanics, remember, or realize that. Never you forget, these are the formulation, nothing else. These are the models. These are not that, okay, you see this, that, it is not like that. And first is our observation. So this is the word observation. One is to understand that what do you mean by the observation. You look into that, there are the only two parameters. Two parameter, we have taken the assumption, two parameters, mass and velocity. Mass and velocity, and if you look into that, if they are observable, again I quote, observable, we have to clear ourselves. What do you mean by the observable? It is very not very difficult. Not the argument. There is no chance that I will argue with you or you will argue with me. That's are observable and all. No, science does not leave any argument. Science does not leave any argument, and whatever the argument we do before formulation. Once we formulate, the argument is stopped. Argument is stopped because with the, and we argue on what basis, that we don't have the information. Now let us collect the information. What exactly this classical mechanics, quantum mechanics, classical statistical and the special theory of relativity, if you look into these only two parameters, if they are observable, the word is very important. Observable, then we call it is the classical mechanics. What do you mean by that? It is meaning of that, and you know that it is all mechanics are based on some calculation. While you are doing the calculation, you will take the smallest mass, smallest velocity, which is observable. Again, that we did not understand till now what is observable. So it is maybe hearing to us it is very confusing. Not confusing, just after this slide you will understand what do you mean by the observable. I told you that science will not leave you to the argue. So the mass and velocity, two parameters, when they are observable, then if you will say that I have built the classical mechanics. Same, the procedure is same, but what we have done, that mass we say that tends to zero. Now the question is coming, what do you mean by the mass tends to zero? Why I did not write that mass is equal to zero? Why it is tends to zero? What is the limit? So that is the question to understand. While I say the quantum mechanics and special theory relativity, I have written here when V tends to C, but mass is observable, we call it special theory of relativity. And when mass tends to zero and V is observable, we have developed the quantum mechanics. This is our assumption, no argument. It is our assumption. By taking this, I'll tell you that how we have assumed. So then the statistical mechanics, when mass tends to zero and V tends to C, then we say that it is, we develop the statistical mechanics. So similarly, we have only four forces. You talk about any force, they fall on that four fundamental forces. They fall on that four fundamental forces. I'll give you the example how it look. If I ask you that what is the frictional force, and frictional force, it is a derived force or a you can say the manifested force, but it is simply we call it is, and people ask the question and make you foolish. What is this force? Basically, it is an electromagnetic force. So I give the example that any force you talk, they will fall either a single fundamental or it is a derived combination of one or two. So this is the fundamental of the physics. Now I told you that I'll fix the limit. What do you mean by the observable? You see, I told you that science does not leave you the argument. In the argument, you look at that, the limit how we have fixed. when the limit comes observable, it is that I will not go to the beyond this, and please you go and read it. Never science leave us the boundary, leave us as the dark. They give the clear picture. Observable means we have fixed, nobody has told us, and it is not this, and we have fixed, we means we all scientists, and together we have agreed that what a human being, what a normal human being can observe, the dimension we call it is the human scale, or observable, or conventional engineering, or you can say the Newtonian mechanics, or you can say the classical mechanics. These are the synonymous to the observable. Just you look at it. Oh, got to bring my pen. Okay, so this is the human scale, that if you look into that, that is you will say that it is, you see exactly 10 to the power minus 6 to 10 to the power 3 kilometer. This is the length it is put in this figure, but don't think that it is only length. All fundamental 7 fundamental units you just write down and put the scale, and that values what you can wait, observe, and remember, modify. A human being what can observe, realize, and modify, that range we have fixed. It is the human scale, or observable, or conventional engineering. Beyond that, you look into that, it is molecular and atomic scale. If you look into here, it is the molecular or atomic scale. Just a minute. Sorry for the interruption. So what I say, that we have the human scale, and so that is from the micrometer. Now I hope all of you understand. I put you the question: M tends to 0, V tends to C. So those things you can clear here. M tends to 0 means it is below microgram, which I cannot measure, I cannot realize, I cannot modify. So that's what we have taken. This is our limitation. So we call it is the human scale. So anywhere L tends to 0, you write. Delta X tends to 0, anywhere you write. Please remember that value is somewhere lying below the 10 to the power minus 6. So you will say that sir is speaking about the electron microscopy, and why did sir is telling about this? And I will tell you that it is connected to there. And never we ask why we call it is the optical micrograph, electron micrograph. Why I don't say that it is the nanograph, it is a micrograph. Remember what we are talking about. Just a minute, I'll just take it. So remember, whatever you are looking to here, here below this world, what I'm talking about, below the human scale, entire world is given the name, it is the micro world. Anything beyond the human scale, or the visible range, or conventional engineering, we call it is the micro world. That's what we use, it is the micrograph. So sometimes we write in our research article or in the book, microstructural analysis on nanomaterials. So the confusion comes when I say the micro analysis, how it can be micron, and when your particle is nano, it is not. And below this range, already I told you, below this range, anything, it is the micro world. So the statement is not wrong. Micro analysis of nanomaterials, it is correct. Why? Everything is the micro. So in the micro world, that is basically anything goes beyond this length. You see that in the quantum mechanics, if you have this, what it is trying to tell you, and what we do, we take a smallest one, then we integrate and say that what is the nature of this block. So in case of the quantum, your smallest one is beyond this observable length, or observable mass, observable time, observable current, observable your charge. So I hope you make understand it is not only the length, and I can replace this with the 7 fundamental, any fundamental unit, then I can write the unit scale and tell that what is my human scale. So like that, the science has fixed, science has not left us that to argue what do you mean by this, and never ever electron can be a classical particle, never ever, because its dimension never falls in human scale. Beyond human scale, I cannot call, or I cannot apply the classical mechanics to explain. But when we put the classical mechanics approach or the human scale approach, we call it the semi-classical or semi-quantum, because you are considering a quantum particle mass is less than 10 to the power minus 6. Okay, it is in the microgram and it is in the nanogram. You have taken that mass and you cannot call it is the classical particle and it should follow the classical model. But to explain who does not know the quantum mechanics, we have tried to give the model, semi-classical model, semi-quantum model, so that people can understand how the experimental observation is explained. So that's what we are taking the help. So now let us go to the electron microscopy. I will give you just one example. You will realize how the electron microscopy has changed our definition, changed our understanding, and which has helped us to the technology. Then I'll come to. So if you look at the dimension of the natural particle, they are in the different size, and you can see in the internet. I'm not going, but you look at the beautiful picture. Till the 1970, you believe me, if you go to the literature, you will surprise. Till the 1970, there were the thousands of explanations on question why this beautiful picture is existing. Not only this, in the nature, beautiful pictures are existing. Thousands of the theory, but we are on not aware about it. We say that the pigment, okay, this color, reflection. People have tried to explain why this observation is coming. So I hope you are realizing as a physicist or a technologist, even if you are a biologist or chemist, you have to understand the science is nothing that the model, and science is nothing but the model to explain the natural observations. If my model is success, then I can reproduce in the laboratory. That's all. This is the technology, nothing else. Very simple. So my beautiful picture, there were the thousands of explanations. So people, like me, and the people confuse which one is correct and what is the thing. So later, when the electron microscope came and they found that, you see, this is in the classical limit. What I want to say, in the classical limit, if you look into your this one, it is continuous in the classical limit. That means classical limit means what I can observe, you can observe. So this is the observable. But when you go to the beyond the classical limit, you found that it is not a continuous picture. It is not a continuous picture. There are it is called the nanofacet, or there are the nano size, basically below micrometer. It is there. It is an SEM micrograph. It is an SEM micrograph. And by the way, you understand why I call it is the micrograph. So now you see that suddenly, you see that I'm answering you as a researcher or a student. You have to be very, very careful. You see, it was a beautiful colored picture, Your information or your understanding starts from here. This is the important things, the sentence you have to buy, that it was a beautiful color. But when I go for an SEM micrograph, it became black and white. What happened? It is only black and white. Remember, your SEM or it is, we are calling it is a micrograph. It is a micrograph. What is that? This is nothing but your XY position, and these are the simple pixels. So that has been plotted. That's all. This is a graph, and the graph cannot have the color. It is only a electron density distribution function graph. Electron density distribution function graph. So for example, the electron, if it is dark, that means less number of electron. If it is bright, it is more number of electron. This is the SEM. But if you go to the what is called in the TM, it is opposite. That also will be clearing in the TM what happens, and in SEM what happens. So that's what I say, that the electron density is different in the two places. Electron density is different, nothing else. It is a graph of the maxima and minima. That's all. Maxima and the minima, nothing else. So that's what, remember, any micrograph, because their color is not existing, that is the visible range. I did not tell that they were classical range or your human scale. What is that? We are taking the help of visible light to observe the things. So visible light, your 7 color is existing here, but not here. Color is not existing here, because in the micro world, all are the density function, probability. You can say the number of probability of number of electrons, or electron density function distribution, whatever you want, you can tell. So that's what always it will be black and white. Anything you go beyond classical limit, there will be no color. Okay, so they will be always 1 and 0. You will say that, sir, it will be confused because you are a young researcher and people put it in a pink, put it in a blue. Some color also you will find. What is that? I told you the 1 and 0. You see that here 1 and 0 is the white and black. I can make the 0 your white and 1 is blue. I can make the 0 is white, and rather putting the blue, I'll put it yellow. So similarly, what will happen? The distribution will be yellowish, means faint yellow and dark yellow. So that's what you get the picture, but never you will get a mixture of yellow, blue, like that you will not get, like you see the original picture. I hope you understand. And the basics of it, then the people could get a particular theory that why it is color. It is nothing but the interference theory of our optics. Visible light, they are reflecting from the different plane, so they do it. I'll not go to the theory. If you try to understand, please go and read it. That's what, if you go for it's a long class, then everything comes, and like I could explain you the technology what we develop. And today 50 rupees, 1 rupee, you are getting very 3D pictures and a beautiful color, and also the color is changing with the angle, and all the technology, whatever you are seeing in your mobile screen and mobile body, all are based on this simple observation by the electron microscopy, and change our definition or the theory, unified theory, why the nature is very beautiful, that could explain by the electron microscopy, so the people could make the technology, beautiful technology, where we are standing today, modern technology. So now let us go that, and we'll understand that how it is done. Thanks God, who began his immense work of creation by giving to heaven and earth this wonderful gift of light, which is visible light, which we can realize. Don't think that we are talking today. God has given the creating this visible light. Don't think, and if he could make our eye within the X-ray, today we have formulated the X-ray. Why? What is the X-ray? You don't think that it is that, and this wavelength we have to said that observable. You argue yourself. So what I can observe, I told that it is human scale. That's all. So that is the thing. And what the material can understand, that is the characteristic. Electromagnetic radiation, we say that it is X-ray. It is not that somebody has come and told that it is like that. So we have divided the radiation or the observation, our observation in the different wavelength in a different category depending upon observation by part. If material observing, then we call X-ray. If a human being is observing, the wavelength can be observable length, we call it is visible. That we have given the name. That's what I say, that science does not give the argument. They have given the name which we have accepted. That is our study. So that's what but we quote it in philosophically. So thanks God who began his immense work of creation by giving the heaven and earth his wonderful gift of light, which has vital importance for the world. Even today, when we refer to birth of a child, we still say he saw the light of the day. This quotation I've taken from the Einstein biography, what he wrote himself. The light is a primary object which helps to see this beautiful world. However, we are not so lucky to see all the beautiful tiny creation. This is the important point where our electron starts. We are not enough because we have fixed that below 10 to the minus 6, I can't see anything. Micrometer, that is 0.35 mm resolution. Our eye resolution is 0.35 mm. So that's what it prompted that can we do something which is beyond the human scale, so that we can understand what is happening at the below human observation, and then we can also create it artificially, so that our beautiful world can be understood, and technology which can be used and make our life beautiful. So imaging, you see that it has not been changed, even if it is the electron. So you have an object, then you have lens system, then the image, magnified image. So this concept is not changed, but what had changed, that the lens we are using you see that in the focus way I'm using the word so that you will not confuse. When you use the lens in human range, that is your optical lenses, then you use your source beyond the object. Basically, source will be beyond the object, so that source will be visible light, so that you can have the object and lens, and it can be fall on that. So, but the question is that I'm just now entering into the concept of your microscopy. When you have a visible microscopy, you have lens system, object, then you will have a light source, visible light, a human scale observable light, then it falls on the lens, and finally falls on the object with a magnifying picture. So now the perfect image to form, I'll go, and you require the three conditions for each point in the project. There is an equivalent point in the image. The object and the image are geometrically similar. If the object is planar and perpendicular to the optic axis, so is the image. This is already we know from our basic of microscopy, optical microscopy, all of us know. So if you look into that, there may be disturbance because of your lens system you use. They may do. So that's what again we call it, is that there will be aberration and all. So your spherical aberration, chromatic aberration, all of things you have gone through your basic optics course while you do the +2 or BSc. So these aberrations we have gone through with the optical microscopy. Nothing is different. When we come to the electron, it has changed from the classical to quantum. That is the electron, but it is there. Okay, so this is a typical that in the eye. Remember what this picture, what it says, that finally it either you go, this is your object. So from the object your ray is coming, and whatever you do here, intermediate image, then you have an eyepiece. Finally it is falling to the eye. Remember, your microscopy directly related to your eye. Why it is eye? Because I have to observe finally. I have to see the micrograph finally. So that's why all of our parameters we have defined, and we calculate or we see respect to our eye, means normal eye, not a particular person, but we have fixed. Again, science is fixed 6 by 6. So the perfect eye that we have put. And if I don't have a perfect eye, I use the glass and all. Again, those glasses are also made and the coating and etc. Whatever just small way we discussed about the technology. Okay, so that's what I told you that. Now let us see it. I told you that always respect to the eye. We have settled our definition. Nothing to confuse or nothing to forget. Ability to distinguish closely spaced points as separate points. Who will separate? The instrument will separate it by magnifying to the eye limit. Eye is my reference. Resolution is the ability to distinguish closely spaced points. That my eye has a limitation, that is 0.35 mm. What it is talking about? What it is talking about, if you have 2 points, that the distance between them, it is 0.35 mm, then I can distinguish these are 2. But if it is 0.2 mm, then I will look that it is not, it is a continuous. Like I give you the example, electron microscopy, it is magnified, then I is resolving that 0.35. But what it is saying, that you have an instrument who is increasing this gap and making it like this. So what is the reference? This is my eye. This is the instrument can understand this and magnify and give to me. So that's what the resolution for my eye and resolution for the machine are different. But machine job is that he has to bring whatever it is fitted, he has to bring to my eye limit, then only I can observe. So the resolution is that ability to distinguish. Who will distinguish? When you have a imaging instrument. Our eye is an imaging instrument. Remember, we have built all the instrument, and depending upon our eye limit. Reference is our eye limit. So the resolution limit, smallest separation of points which can be recognized as distinct. The principal region limiting the resolution is the diffraction of light waves. Diffraction spots from nearby points may overlap with each other. What it is saying, very, very important understanding what we are talking. When you have the two lines and the suppose a source of the light is falling on like this, so what happens when they fall here, and depending upon this, the way it has a particular wavelength, we know that the edge of this, if it is comparable with the wavelength of the light, then you will have the diffraction. So when you have the multiple diffraction, then you cannot see it distinguished. So that's what it is saying, that if your wavelength is very, very less, it is very, very less. When your separation is less, so your wavelength has to be less, so that you can limit the diffraction. Okay, otherwise it means in the visible light its wavelength is more. So what it is happening, that while it is falling on the here, and they are unable to do that, so that's why it is feeling like a reflection and diffraction due to the diffraction limit. Can't distinguish these 2 points. Okay, resolving power. Now the real story of the eye reference, the resolution achieved by a particular instrument. You look into that. In a particular instrument we have built, either electron microscopy in this, and under optimum viewing condition, that is maximum magnification, that is the resolving power of the eye by the resolving power of the microscope. So this is the important. So but again, question, how small you can see with the optical microscopy. Okay, so these are the some basics that you can realize. If you want to really understand, please go back. I don't have time to go these basics, and you will see that the aperture and resolution, where it is going through. So those then the resolution, it depends upon the aperture, and this theory we can develop, but I'll just directly I'll go. This is the Ernest Avi formula. Please go through it and you will understand, but directly I will tell and go what exactly we do it. Okay. So Ernest Avi, what it is saying, that if you take, and that is the R is equal to resolution power, and so whatever I show, that is the derivation of basically Ernest Avi theory, and some of you may know, or if you don't know, and please go through it. So R is equal to 0.61 lambda by eta sine alpha, that is or sine theta. So theta is the angle. I'll show you that angle where the light is incidenting upon the object. Eta is the refractive index of the medium where light is passing. 0.61 is the your constant which we derived and what I showed you in the beginning, and I cannot go because it is time is very short. So the lambda is the wavelength. This formula, you look into that. Ernest Abbe told that it is nothing to worry. It is observation. It is the observation. Then the formulation has come. What is the observation? You just you know that anything. I'll just take only 1 minute. You will understand easily. So you have a light wave. You look into that. This is one packet of the light. We say that it's new. One packet of the light. Now what it is happening that suppose you have an object here. So this light is falling here, right? This light is falling here and you have the two objects. Now you look into that. Sorry. Okay, fine. So you look into that. The wave packet h nu is reflecting from this, and the h nu is reflecting from here, and they are the different. Okay. So that is the what I'm talking about. This is h nu. This is another h nu. So the reflection from one point, and again I'll put it very. Suppose you have a block like this, another block like this, and they are separated like this, and you have a wave like this. You see, now you can easily see. So now you look into that. This is h nu. This is h nu. So that if you have an instrument like your microscope, they can distinguish this and distinguish this. But if they are very close, so this is the formula what we are talking. If they are very close, if your wavelength is like this, now you see that same h nu is coming from here, same h nu is from here. So you cannot distinguish. It is the same. That was the argument of the Ernest Abbe. Okay, so he said that if it happens that half of the wavelength, what he said, you look into that. Suppose if you have a wave like this, even though they are the same packet, but one is plus half, another is minus half, if they are separated with the half of the wavelength, then you can distinguish. So that was his argument. Then experimental also it is proved that it can be. But what happened when the Raleigh come, he said that he argued that why are you taking the half and you are distinguishing? Suppose it is like that. So he said that it is the full width half maximum. If it is beyond this, if beyond this, so that means you can distinguish. He said that not half, only the full width half maximum. That was only argument, very simple argument, and also the experimental it is proved. So what we say now, this formula is modified like this. It was earlier, it was lambda by 2, but this is, you will find that it is just a correction factor, but not much difference. I spent some time to make you understand exactly what is happening, the resolution, and what we defined that it depends upon totally wavelength of our light. This is the wavelength of our light. Okay, and the refractive index of the medium and the theta. Very interesting. So that if you calculate by taking, you see there is an example, and 200 nanometer, the visible light is around 200 nanometer. If you take, or the shortest wavelength is 450 nanometer, then you will see that resolution is 187 nanometer. That means if you have the object is either 187 nanometer size, means this is 187 nanometer or bigger than this, then you can observe by a optical microscopy. Or if the two objects are separated by 187, then also you can see that there are the two objects. That is the conclusion, that in the visible light we can go up to the around 200 nanometer resolution. Beyond that we cannot see anything. Okay, so then the people thought that, okay, I can take the, if it is only wavelength, I can take the different wavelength. So you look into that, the X-ray wavelength, it is much less than the visible. Ultraviolet is in between also. So it is 0.01 and the 10 between that range. So then they say that if you take the copper K alpha only 0.15, then your resolution will be very, very low by 2. Simply you just think about by 2. That I can go, it was the 200 nanometer for the visible light, but I can go up to the 0.07 nanometer if I use the copper K alpha X-ray radiation. Okay, if you don't know the copper K alpha radiation, you forget it, and you just take that 0.1 nanometer is the starting X-ray wavelength, and you can go up to the 10, and so in between there are, you take the 1 nanometer. Okay, 1 nanometer by the way, you can say that roughly that 0.5 nanometer, and you can read the X-ray, you can see the length and etc. So please don't confuse that electron X-ray micrography. In case of your medical science, it is totally different what we are talking. Don't compare it. In their technique is different. Although I know that, but I cannot explain you due to the time limit. If you want, I can do. Actually, I take the medical physics course, so I know that. So that's what we understand that limit is very very low. So that's what the people understand the electron. Let me go back to this. I'll not go here. So just a minute, I'll go directly there and we'll come back. So what I'm talking about, the wavelength of the electron, it will depend upon what? Let me say that how we get the electron. From here we will understand we have the 4 kinds of the electron source. We know that thermionic electron source, we know the field emission electron source, we know the optic with your photoelectric electron source, then the secondary electron source. I'll not tell you the technique, and please go through it. But whatever it is, you get a electron source, and it is a example of the field emission electron gun, and where we have applied a small voltage and we create a electron plasmon here, then you apply a high voltage, this electron will start traveling. So when they'll start traveling towards the anode, while they will come with the high velocity. So now you have to make the arrangement so that rather attenuating at the anode, they should go out. So when they go out, and we have a source, that's all. You have an electron source. So that arrangement we have done. This is the example of a field emission electron, but you can do it in the thermionic emission also. You just heat it. So what will happen? There will be a plasmon, electron plasmon. Any means you have to create the electron plasmon here, then you accelerate it. So that is the fundamentals of the electron source. So when electron source comes out, so what it does, and depending upon the accelerating voltage, this voltage 100 kV, so its wavelength is h by mv. You look into that. It's a small you can see the small derivation that the kinetic energy half mv square of the electron will be that you have applied, voltage you have applied, which is nothing but the kinetic energy of the electron, traveling of the electron through this here. So depending upon the voltage and EV, so this will be velocity of the electron. That velocity, now you look into that. I know the mass of the electron, because this electron is there is no force, it is a free electron traveling. So m0, then h is the Planck's constant, and v is the velocity. This is the wavelength of the electron. If you look at, calculate, and just put the value of the Planck's constant and mass of the velocity, and finally you get something. You look into that, it is the velocity will be convert from this equation. V will be, and it will be m ev square by 2, then v will be 2 ev by m. You see that v will be 2 ev by m root over, then you put the value and other electron charge of the electron, then mass, everything you find in terms of this is capital V. So this is V, this is the capital V. So you will get that this in terms of the 1.23 by root V. Very simple. Our physics formulation, we see that lambda is equal to this. Now you look into that. If you take the relativistic mass, m is equal to m0 by 1 minus v square by c square, then you get this value. Then finally you put the voltage, and calculate the lambda. You see that the lambda is also, even if with the 50 kV, it is less than the X-ray. So the wavelength, you can tune depending upon the voltage, 10 kV, 50 kV, 100 kV, 1000 kV. So with the voltage, I can control the wavelength, so that what will happen? My resolution, lambda by 2. Resolution is close to lambda by 2, less than lambda by 2. but it is close to lambda by 2. So you can see that even if a 10 kV electron, if I can do the microscopy, I can get 0.06 nanometer resolution. You look into that, what is the length scale? It is the atomic length scale, even if 10 kV. Unfortunately, we have not reached that. Even if in 200 kV, we are unable to take 0.06. Why? So the reason is very simple. Our technology has not advanced in such a way that to control the error-free electron source and the error-free imaging, we are unable to do. Very interesting. I told you the second question, what are the microscopy we can build? Listen carefully. Within 2 minutes, I'll make you understand. Very simple. When the electron is coming, you have a sample. This is electron is bombarding. So electron does not understand what is happening in this thing. Everything we do it. So we are formulating. When it will interact with the atom, so what it will happen? Some of the electron will pass through. If it is less than 100 nanometer, if it is a 50 micrometer or 1 micrometer, no electron will pass through. Zero. So if it is less than 100 nanometers, some of the electron will pass through. So this area is the electron transmitted through your sample, and some of the electron will be in this area. This is the basically your reflected electrons. So now we call that is the scanning. We have built the scanning electron microscope in this area, and we have built the transmission electron microscope in this area. So now what we conclude, what kinds of microscopy we can have? Only SEM and the TM, nothing else. You look into that, everything has been written down. When the electron interact with the material, or that is material is nothing but the atom, nothing but the electron cloud. That is our assumption. So when it is interact with the electron cloud from your material, so this phenomena takes place. What are this phenomena? Very simple. You look into that, when electron comes here, they may face to a nucleus. So there will be the backscatter. While I say the backscattered, the energy of incident electron and the backscatter electron are, listen carefully when I say very simple information, they are the almost equivalent. Backscatter electron and the incident electron, their energy is almost similar. Then what other happens? When electron falls on the atom, what will happen? The outermost electron, the electron will observe here. The incident electron observe here, but from the outermost electron, one electron may come out. So what I will give the name? Secondary electron. Now you see that the electron is observing, another electron is coming out. So its energy will be less. They will lose the energy while the observant ejects the electron from the outer cell, because it is the binding energy. They will lose that much amount of binding energy, and their energy will be very, very less than the incident. So incident energy will be, so incident energy will be equivalent to the your backscattered electron, and intensity will be much greater than secondary electron. You see that this information, how it will help us to build the microscopy. Now you look into that, when electron will fall, when you have the atom. So do you think that it will be strike to the only outer? No, it may strike to your inner. Very simple. This is our assumption. It will be strike to the inner. So when it will be strike to the inner, and you know that the energy difference of the K and L cell are falling on the X-ray. That is the material characteristic. We have fixed X-ray. So that what it will happen, this electron will transit to this. Then they will be, the lifetime will be very less, and they will come out. So X-ray will come out. When the electron strike to the inner cell, the X-ray will come out. But what will happen to that electron? Then that electron, while it will go out, they will strike to the outer cell. Now you look into that, your secondary electron, and the electron, either it will be eject from your outer cell, or it will be eject from the inner cell with the multiple action. X-ray, then it will be eject. So this effect was observed by another scientist, and I will tell you that the amount of electron is coming, only 1% strike to your inner, and again 1% of your inner will eject the other electron. That means if you have 1,000 electron, 100 electrons will be in 1,000 by 100. 10 electron will be I can put another one so that it will be 100. If you have 10,000 electron incident, only 100 electron will be, probabilities that 100 electron will be strike to the inner, but only one other electron will come out. This is the ratio probability of the electrons. So the other electrons are very, very less, but they are specific. They are specific. They will be depend upon the KL shell of the atom. So that's what we can get. We can get the other electron, backscatter electron, secondary electron. I leave to the audience. If anybody can think there is another kind of electron, I told that electron will come and interact with the atom. So it will be strike to the nucleus backscattered, or it will be interact with its electrons on the cloud and do it. That's all this can happen, phenomena can happen, nothing else. So that's why you will get the other electron, already I explained, backscattered electron, secondary electron, then your characteristic X-ray. I told that while the other electron comes out, the characteristic electron X-rays, then there will be lots of multiple transitions of the electron inside the atom because of your electron bombardment. So visible, and it is not written here, UV, all other kinds of spectra also will come out. You don't have control. All things will come once the electron falls on the sample. So when they pass through it, what will happen? This is the atom. While pass through it, they will be facing the potential. So they will lose the energy. So while they will lose the energy, they will give you the Bromston X-ray. That is that electron passing through a variable potential, they will keep on losing the energy. That H nu is nothing but your X-ray, continuous X-ray. So that's what you will get, a continuous X-ray. That is the scientist again, it's given them, continuous X-ray will come out. Then they will lose the energy, so that will be inelastic scattering. And some of them will not lose anything in direct beam. Then some of them will be scattered elastically, energy conservation. So that's all the possibility. There is no other possibility. Okay, so whatever the phenomena I discussed, and this is happened when an electron interact with your material. So we are restricted the electron microscopy on this. We have the other electron microscopy. We have the backscattered electron microscopy. We have secondary electron microscopy. We have X-ray detection. We don't bother about the visible UV and etc. So then here we use the elastic scattering electron and inelastic scattering electron. I told you that. While they will go with this potential, they will lose the energy. So I can compare this inelastic scattering with the incident electron, then I can find out how much energy it has lost. So that really depends upon the chemical environment of the element. So now you see the application. Once I understand this, very simple. We have built the inelastic scattering electron. If I can observe this, now you look into that. The energy of all the electron source are different. So only specific detector to detect that energy electron. So then that will be separate. Otherwise, all other arrangements are same. So that what I say, that inelastic scattering, they can say that what is the chemical environment that we have built to the yields. Okay. Electron energy loss spectroscopy. I'm starting one by one. Direct beam. If you have this, and if there is electron, then this electron cannot reach here. If no electron, it will reach. So I will get a black and white means image of the sample, direct beam. That's what the TM imaging we do. There are the other things, and I'll comment. So we don't consider this way continuous X-ray. We use this characteristic X-ray for the characteristic. Particular element will have a particular kind of the X-ray. We call it is the characteristic. So we can find out what kind of element is present. That's what we say that energy dispersive spectrum. Energy dispersive means that characteristic. Particular element will have a particular X-ray energy, that we can look and see that how it is what are the elements present in our sample. So that's what we call it is the EDS, secondary electron for the imaging, backscattered for the imaging, and agar electron for the, it is characteristic electron. It is not the reflection. If you go for the imaging, you have less number of electron, imaging will not be very good because it is the electron density you are going to measure, only the electron density on your sample. So these are not used for the particularly for the micrograph there, but they are used to find out the percentage of the element present in your sample. I hope I told you the entire story, what the electron microscopy is doing for us. These are the applications. So now the question is coming, how we'll build, and we'll go. The first little bit I'll go because we have only, I think I have only 10 minutes and I'll finish it some of the micrograph, and nothing to go because almost I told you that what the electron microscopy, and another is the optics, electron optics. Very simple. It is an electron. I cannot use a lens, means your glass lens or something like that. So what I have to use, I have to use an electromagnetic lens. That's what either it can be a electrostatic lens, and this thing, nothing to worry, whatever it is. So many things is written, but very simple way you understand when the electron is going and there are the different potential. So depending upon that, F is equal to, very simple, F is equal to Q P cross B, if it is in the magnetic field and if it is in the electric field. But if it is in the electromagnetic field, we write QE plus QV cross B. Very simple formulation, but very powerful. What is that? And you know that we accelerating electron, it has a particular velocity. Then depending upon the potential E, depending upon the magnetic field, depending upon the E and V, its path will be different. That's what engineering we have developed. Okay, we have developed the engineering that is called the lens system of the your magnetic lens, electrostatic lens, and also electromagnetic lenses. So I'll show you. If you look into that, what we have done, and I did not go, and we have done that in the magnetic lenses. We have made the modular, because if one is gone wrong and others can work, at least you can have the image. So that's what we are not, earlier people are using the single coil and single magnet, but now it is a modular magnet. Now let us see that exactly. I told you, your microscope, optical microscope, or your projector, and an electron, you see the path, it passes through the electron, and like a cyclotron, it forms like a cyclotron, and it focus it here. Depending upon the magnetic field, focus will be here or here or here. Now you see that same magnet, and with the current and voltage changing, you can change the focal point. So that's what your image can be, having different magnification. So now you look into that, its focal length is kV ni square, and F is the focal length of the lens. K is a constant, that is the engineering constant, always it comes. It is a different story. If anybody wants, I can explain, but not right now, we don't have time. So B is the accelerating voltage, and Ni is depending upon here the coil. Okay, number of turns and the current in the coil. So depending upon, and one can find out the focal, sorry. So, but there will be the defects. I told you, chromatic aberration, spherical aberration, it can happen. What I were talking, and your voltage fluctuation, current fluctuation, and while we are putting on the picture, it is like this, but it may not happen. So we have taken ideally that this path is fully evacuated, no gas and nothing, but it may not happen that way. So that's what those things, engineering parameters, they create the defects in electron lenses. So that's what we get the aberration. The question is that why do one should understand there will be the aberration? Because when you get the micrograph, one has to analyze it in that way, that what kind of aberration it has come. Okay, so there are so many chromatic aberration, and due to the different voltage fluctuation, then the energy loss due to the inelastic scattering of the specimen. So this chromatic aberration comes. I'll not go to this. And axial astigmatism, it may happen that your voltage, whatever the high voltage you have applied, if it is not properly synchronized, then it will give you the astigmatism. That figure will be, what will happen, that the figure will be drifted towards left, right, up, down, it may happen. So that's what I told you that we have built. Let us see the transmission electron microscopy. I'll go, means this is there, and I told you that same thing, but I'll show you this. If you look into that, very simple. It is not very different, and your electron source then travel with the lenses and multiple lenses to make it. That is the column. It is a condenser or the collimated lens, like our optical microscope we call, and your sample is here. Then you have X-ray detector here. Then you have other lenses for the objective lens like your optical microscope. Then finally you detector, it is a camera or this thing. So that is the schematic. And if you look into the micrograph, and it is the GLTM, and you see that it is the column and electron is going, and finally there is the camera here. And if you go anywhere, you'll find that. And the concept and machine, more or less, for all the companies, it fall like that. Okay, so these are the specification for this. It is a 200 kV, but it is a what is called that your thermionic emission gun, and we call it is the dirty electron. That's what its resolution is a little less, but it is good enough to look at the atomic resolution or means lattice and etc. So if you look, these are the ray diagram. There are the two kinds of, and one is the selected area diffraction, and another is the imaging. And I don't have time to go, and this is side by side. But when you go to the TM imaging, you have the two techniques. One is that it is your bright field imaging. It is a very, very important, and that is the dark field imaging. Again, dark field, it is off axis and on axis. What it is saying, when you see that it is in an electron, while it is passing through, there will be diffracted. It is the direct, and this is the diffracted, and the diffracted pattern you will find here. You look into that. If there is an electron, and it will be bright, because the diffraction, it will be bright, and when it is an electron, it will be dark. Because if the electron cannot pass through it, but electron can diffract. So that's what this spot is bright, but your electron, if it is in the path of the electron, it is the dark. You look into that, this is dark, this is bright. So either you take this dark and say that this is an electron, or you take this one and say that this is an electron. That's all. This is the difference. So you have to put an aperture. Aperture means it is just a metal plate which will just attenuated. If there is electron coming here and there attenuated, and only focal point will be focused. That's all. So that's what it is, the bright field, because the electron, I told that if you plot it, here it is a dark means electron is here. That's what we, and if there is a bright means we call electron is not here. So that's what your background will be bright and your sample will be dark. I take the example only one electron, but it can be sample. It can be sample. So that's what we call it the bright field. Bright field means your sample is dark and field is bright. 1 0. Okay, I told you 1 0. Bright and the dark. So then there will be the dark field means you look into that, your diffraction you are taking. Either electron are in this axis and diffraction you are taking here, or you make the electron in an incident after knowing this theta, then you can take the image. You see that I have taken the bright image. Bright image means where the sample is there, you will get the bright one. So if you take it, this will be your bright and this will be dark. This is your sample bright and this will be dark. So where it is required, you look into that. When you have soft sample, if your sample is soft, you look into that, the electron will pass through it. So this dark point will be very bright. Okay, and it will be brightest, and this will be bright too. So that time distinguishing this figure, it will be difficult. But if you take this image, if your sample is soft, and this is the better, because you will get the bright and this will be completely dark and this will be a little bright. So you can distinguish. That's what if sample is soft, like your biological sample, polymer sample, then better go for the dark field image. But if you have a metal, better to take the bright field, because metal will not pass an electron through it, so that you will get a very good black spot on your bright background. So that's what this is the two techniques we have developed. I'll not go through it because it is this. And TM, you should look into that. If you go the image, then we get this morphology, defects and phases, structure and defects and interaction surfaces, then symmetry and strain lattice parameter, elemental analysis. Already I told you that the effects, yields, EDX, and these are the diffraction is already I show you the bright field, dark field, and the diffraction can be utilized in the different way that this you are using for the imaging. But if you take the resolution of the electron, an atom, so then sorry, it will be your diffraction. It will be your diffraction. So that is the high resolution imaging, lattice fringing, and electron diffraction. It is entirely different from this, but I don't have time to distinguish these two. It is entirely different, but these are the almost all. That is a scanning. I can do the scanning electron microscopy also here. Okay, what? And I can have a sample, and I will make a small spot, and I will scan all these points and do a micrograph, and it can. So if I go that, you look into that, I show you that if you see the picture, and for you right now may not be okay, so all are looking same, but for export, it is the exactly focus. But this is a under focus, this is a over focus, really. And if you look into that, it is a dark field image, biological sample dark field image. These are our image, and you can see there is this is a carbon nanotube, and you go to the high resolution, you'll find the walls are here, the carbon nanotube, these are the proteins. So like that picture, you will get the beautiful picture. And if you look into this picture, how the nanoparticles chain is formed, basically nanoparticles are forming the small, and when you are growing those particle, you look into that, this is the in situ, how they develop, gold nanoparticle develop, bigger particle, and they're merging and forming the bigger. And they are the basically core cell. You can see this is the dark bright, you can see core cell. Silver is here, silver is there, and over gold coating is present. So these are the bacteria, biology, and the dark field image. You can see bright field. So high resolution, if you go, and you will get the lattice fringes. We don't get the lattice, and I don't have time to tell exactly that why you are not getting. And I hope if you have any confusion, and I'll explain. And anybody interested, you just write me, or after this lecture you can ask me, I'll explain. Let me finish. So the electron diffraction, you know that electron is coming here, and you have a specimen here, then what it will happen, that they will be diffracted, you will get the diffraction spot. So this is the simple formula by which we say that where you will get the diffraction pattern. Okay, diffraction pattern from the lattice. So if you look into that in the diffraction, what you get, if you have a polycrystalline sample, you get the ring. If you have a single crystal, you will get the spot like this. So you can see the means it is a polycrystalline, and this is a single crystal. You can see the either sample is polycrystalline or single crystal or amorphous. You can also distinguish. So you know that if you look into that, all the peaks, the same sample, the XRD peaks, they are matching each other with the one diffraction pattern, different diffraction pattern, same as with the XRD. Beautifully this TM, and it is making, and you can see the points, and with the diffraction and all those things you can do with the machine beautifully, you can measure. If you look, notice all the pictures are black and white. I told you. Why is the black and white? Because these pictures are the very, not the what is called color. You cannot make it because they are below the classical range. I'll not go here that what happens, and that you can have the STM scanning transmission electron microscopy here. These are the mostly biological sample, and where if you are electron, you are falling, if electron is burning the sample, and those samples and these will be helpful, that you can make the spot wise, you can take nothing else, just spot wise you take, not that at a time to put, and no difference, same the transmission electron microscopy, but you can make the very small spot and take the picture and combine it. That's all. That is the scanning tunneling electron microscopy. Scanning tunneling electron microscopy, I told you that yields that, and the electron comes, interact with the atom, and they lose the energy. You see, they are losing the energy. If I can observe this, and I can find out what is the environment of the metal depending upon the different material we have. We know the theoretically what material will have what. So this is the arrangement. Again, the instrument part I am not going. You will be confused. So, but you get the different yields spectra from where you can say the electron cloud or the electron environment of your material. Okay. So fine. So this is I'm not going. This is all about the electron microscopy sample preparation. I cannot tell. And let me just summarize that in the sample. If you have the powdered sample, you are lucky. You can put it in the TM grid and do it. But if you have the hard samples, then it will be very difficult to do with the TM, because you have to prepare, because you, your limitation. Let me just tell that what happens. Limitation is your 3.05 millimeter. 3.05 millimeter is here. You have to put the sample. This goes to the machine. So 3.05. That's what you have to make the sample. If it is hard, you have to make the 3.05 size. Then remember, and there the process that is like the ultrasonic cutter. If it is a hard sample, you have to use this. If it is a soft sample, you can use this disc punch. Then you have to do the dimpling so that your sample, if you have a sample, then what a dimpling is doing. So you get a sample size like this. So you make it less than 0.5 mm. Then you go for the pips ion milling. So finally your sample will be like this. Your sample will be, there will be a hole, and there the thickness will increase. So this area you can have a TM area. You can see the TM. This will be, sample will make a hole. Basically it will be like this, a hole. Then this area, okay, this area is nothing but this. Okay, so you will have the different thickness. So there you can look it. And if you have the biological sample, again you have to do a special preparation, like you have to staining and do it so that you can use it. I'll have to go through this, and I'll go scanning electron microscopy. Already I told you. Now you look into this. You have this source. Sorry, time is not there. 1 minute, but I'll try to complete. Bear with me. So because it is very large, so that if you look into this electron source, there are the lenses. Your sample is here. You don't have to go beyond this. So sample is here. So what we do, and this electron is coming out. You see, electron is coming out. That's all. So the question is that either it is the secondary or BSc or Auger electron. What you have to do, you have to put an electromagnetic field here. So F is equal to Q, V cross V, QE V cross V, and you can tell only V cross V. So the velocity of backscattered electron is different. Velocity of scanning your secondary electron is different. Velocity of Auger electron is different. So depending upon the field, so only the particular electron, they can be attenuated in your, they will be attenuated to your body, but a particular, depending upon the voltage, your field here, particular electron will go to your detector. So either you can detect secondary electron, or you can detect the backscattered electron, or you can detect the Auger electron. So separate, who will control? Only the magnetic, electromagnetic field here. Electromagnetic field here. That's all the difference technique, nothing else. So I'll not go to that resolution and all. So this you will find this kind of machine nowadays. This ball thing you will not get. This is the liquid nitrogen. Nowadays it is coming the self-cooling, like the Peltier cooling. So you get the machine and like this. And this is the modern machine that you see, that X-ray detector is here, but cooling is not there, because when electrons strike to the electron detector, so there may be the heat, that's what they cool it. But nowadays it is the self-cooling, that is the Peltier cooling. So you will get the ACM. You see that this, it is the end here. So just sample is here. So in the DT, that's what the price it increases. So here, what is that? If you take a magnetic material, and there may be astigmatism. If you are talking, there may be astigmatism. So that's what, when you see the picture, so you can realize. If you have a magnetic contamination, you look into the contamination, your picture is that. Means why I'm telling you that as a researcher or this thing, you have to understand that electron, your sample is supposed to be here. but due to the contamination here, and it is like this. You see that same sample, and these samples, and you have to be careful while you are taking. And the image distortion, you see, image supposed to be round, but now you see that it has been be distortion because of the electric field, magnetic field around, or somebody is making mechanical thing. And brightness contrast, you see, and while you are taking the picture and same picture, but the brightness contrast is different. So you cannot do outside, you have to do inside this. And if you have magnetic field, and you see that how the picture can disturb. So this is too much. And mechanical vibration, how it can disturb. So that while you are getting the same picture, you can realize that it is the user has taken properly this or not. Okay, so these are some of the picture to realize. And this is, by the way, this is our picture, and I want to show that how beautifully, and the you are taking this our tomato and this ascorbic acid. So it looks to you very simple, but they are like basically fiber, and we call that, okay, this food is fiber. And the people ask that it is I can't see that this is fiber. Fiber is in the very different order. So these are the basically the, you can say, these are the bacteria, sorry, CDS nanoparticle. And why I have shown this, because that electron is coming. If it is not, these are the semiconductor, they are charging. Charging means electron is coming, sitting on the surface, because these are the semiconductor. Electron cannot attenuate it to the base of the your machine. So that's what the electron is accumulating. So there is brightness means more number of electron, basically electron density is more. So that's what I told you, that dark field image in TM, that means bright field image in the TM sample is dark, but in ACM, if your electron density is more, your sample will be bright, because they will be reflect from there. These are the some pictures. So fine. So already time is over. I don't know how much message I could pass you, because I have to go fast, and some of them I omitted because of the time. So let me read. Electron microscopes are at their service to explore the natural phenomena. Electron microscopes have helped to understand and nurture the modern technology. Two kinds of electron microscopies: reflection mode, that is your ACM or other electron microscopy, etc. Then transmission mode, that is a transmission electron microscopy. Details, morphology, and chemical constituents of the materials can be characterized by the electron microscopy. Each electron microscopy technique has its own advantage and disadvantage, and which did not get the time to exactly go through it. And the electron microscopy needs more attention to serve for the modern technology, because we showed a 200 kV TM, but its resolution is 0.02, but it is supposed to be 0.0002 or 0001. But we are, due to the technological difficulty, we are unable to do. Then electron optics and visible optics are similar, but need different technology. Thank you for your attention, and also thanks that you have not slept or something. So thank you very much. And if you have any question, already I have taken 5 minutes more. I'm sorry for that. If you have any question, and I will be happy to answer, please.
Anybody wants to ask question to sir?
I could
We
not
checked
look-
that one. I think
Yeah, sir, Astha is there. Astha, you want to ask something? Hello.
They can
Sir,
write.
yes, sir. Shall I share your email to
They can
participants so
write
that they can
also.
write? Yes, sir.
Uh,
Sir, I'm asking for your email. Shall I
no,
share
but
your
I'm saying that if there is any queries, so people can write in the chat so that.
chat? Yes, sir. But now they are not interested in writing in chat.
this happens. I don't know how much they were attentive, and this thing. My email ID is here. I hope you are able to see. My email ID is very simple. Only 4 letters @itp.ac.in. MANO, 4 letters.
If somebody replace N to M, it will be nano.
Yeah.
So from that we can recall it quite easily.
Okay. Okay. Nano is very interesting.
Yeah.
Sir, participants are asking for your PPT. Can you share this?
Definitely. Definitely. I'll remove these photographs because this will be a huge resolution. Then I'll send to you. Okay.
Okay, sir. Okay, sir. So now I request Dr. Tanmay to present vote of thanks to Dr.
Yes.
Sir.
We are really thankful to our speaker for receiving our invitation and delivering a wonderful talk on the basic fundamental of this working of electron microscope, starting with the difference between the classical and the quantum mechanics, and what is the necessity of electron in place of this optical microscope, and also explaining the instrumental setup as well as also differentiating from the image how it will be correlated to our research. So we are really thankful for this wonderful session, sir. And I hope all the participants must have acquired the basic knowledge about the electron microscopes, and they will definitely incorporate this in their research. We are really thankful, sir.
Thank you very much. Thank you.
Thank you so
Okay.
much, sir.
Thank you. Thank you. Shall I log out?
Yes, sir. Yes, sir.
Okay. Okay. Thank you very much.
Thank you.
Participants, tomorrow Dr. S.K. Raut from BIT Mesra will deliver an interesting talk on impedance spectroscopy. Again, the time is 12. So please join sharply at 12 and we will
Let them join 5 minutes before.
5 minutes
That,
before.
that will
Okay.
be better because we are every day we are losing 5 to 10 minutes.
Okay. So please join 5 minutes before so that there may not be any mess. Okay. So and I'm sharing the feedback form. Please submit and please fill and submit. Okay. Thank you. Thank you, Tanmay sir.
Ma'am,